Hello chemistry people, it's Miss Byrne here. I'm here to talk to you today about some theory in the higher level atomic theory course, particularly using convergence frequencies and the Planck equation to find ionisation energy. Now, when you look at the course outline, there are some key ideas. What we're going to be looking at particularly today is this first point here, looking at emission spectra. We're going to be solving problems using E equals h nu. We're going to be looking at convergence limits. Okay, so let's start with some recapping. So let's start just with some basic light and electromagnetic spectrum if you want to play along while following in your book. So let's look at some basics about what a wave of light looks like. So when you have a wave of light, remember it's this transverse wave. We have our wavelength, which is this distance here. Now that's normally given the symbol lambda, and its units tend to be in nanometers. Remember, nano is 10 to the negative 9. We then have frequency, which is given the symbol nu. It looks like a V, but it's a weird V, and that is wavelengths per second. It's measured in how many wavelengths we have per second. Okay, so we've got wavelength and we have our frequency. So frequency is measured in cycles per second. We have our Bohr model of the atom. Remember, the Bohr model was the one that had our nucleus in the center. Remember, our nucleus has that positive charge, and then the rings of electrons around it. Now, if we take, for example, looking at these two energy levels and just rotate them, we end up with our electrons, sitting here, and I might change the color of my electron quickly. So we've got our electron sitting here. Now, if I give that electron energy, it can jump up to this higher energy level. But then, so let me show my incoming wave of light, and then with that little bit of energy, my electron jumps up, but then my electron falls back down to this initial energy level, and it releases that wavelength of light. Now, I know I'm saying light, but of course this could be anywhere in the electromagnetic spectrum. It doesn't necessarily need to be in that visible spectrum. Now, in terms of naming these levels, if this is my ground state, this is called the n equals 1 energy level, and let's say it's jumping up to the n equals 2 energy level, the next level up. Okay. And we've got a little bit more recap, and this is based on the ionisation stuff that we were looking at in periodicity. Remember, it's the energy required to remove 1 mole of electrons from a gaseous atom in its ground state. So my electrons are sitting on those lowest energy levels that they can sit on, and I'm trying to remove one of those electrons. So back before, I said that my electrons, when they're in their ground state, it was n equals 1. There are then a number of energy levels above where that electron can jump to. Once I reach the point where that electron is no longer being held by my atom, that is called the n equals infinity energy level. It is infinitely, as far as the electron is concerned, far away from that atom. So the Ionisation energy is the energy it takes for me to take an electron that's on that n equals 1 level and move it to that n equals infinity level. Now, this is all well and good, but we actually have to figure out how we work this out. So let's start with the Lyman series. Now, you may or may not remember this, but the Lyman series is one of the emission spectra of hydrogen, and its light waves are in the UV range, so just outside our visible spectrum. And this is a picture of our Lyman series. Remember, so see here we've got our n equals 1 level, which is where our electrons all want to return back to, and we have this n equals infinity level, which is where they're removed. Okay, so what can we measure here? We can measure, as our electrons fall down, we can measure the wavelength of light that is coming off them and the differences between them. So we can measure the wavelengths of light. Now, that is useful in and of itself. However, where it gets really interesting is what we can do with it. So what we can calculate is we can actually calculate, let me just grab another pen colour, the differences between these levels. So I can calculate the difference between the third and the second energy level, the second and the first, and the fourth to the third, etc. So I can measure the difference in both wavelength and frequency. So just thinking back, when we look at the wavelengths, that would be our absorption or emission spectra. So on an absorption spectra, it would be that rainbow with the black lines in it showing the wavelengths of light that are being stolen. In an emission spectra, it would be that black box with the lines on it showing the frequencies of light that are being emitted. So more on the Lyman series. What we can see here, and you may have seen it as I was drawing, as my n increases, the difference between the energy levels becomes smaller. So this difference 5 to 4 is much smaller than this distance 4 to 3 is smaller than 3 to 2 is smaller than 2 to 1. Now, what that means is that as those energy levels get higher and higher, those numbers converge. They come to a single point. Now, that convergence limit is really important because as that number approaches 0, it means that that electron has less and less far to jump. And as that convergence limit reaches 0, it means that I've reached that n equals infinity energy level. So let's actually just look at this number, look at these data in a slightly different way. Okay, still on the Lyman series, and this is one of the massive NOS points out of this atomic theory section. If we're going to do science accurately, we really need quantitative measurements. This is so we can analyse things mathematically in order to see patterns. So while it might be obvious just looking at something that there is a pattern occurring, until we have the numbers, we can't really show that there's something happening. Now, this table has been snipped directly from your textbook. So what is this table telling us? This is telling us that at the excited energy level that n equals 2, the frequency of light that is emitted when my electron drops from 2 back to 1 is 24.66 by 10 to the 14 per second. Now, this delta V is saying what is the difference between these two numbers. So 29.23 by 10 to the minus 14, sorry, by 10 to the 14 is subtract 24.66 by 10 to the minus 14. The difference is 4.57 by 10 to the 14. Okay, let's actually graph some of this data. So let's look at what we mean by convergence limits. I explained it briefly the other time, but it's much easier when we can actually present this data in a slightly different way. So what we're looking for, the whole point of this is to find the frequency at which my electrons are removed. They're taken from that n equals 1 level to that n equals infinity level. So there's two different ways graphically we can show this, and here's the first way. We have frequency, which is that new character, versus the difference in nu. So we're looking for the point at which our change, remember those energy levels get closer and closer and closer together. When that equals 0, there are no more energy levels to jump between, so that electron must have been removed. So there's two different ways we can look at that. You can either sketch this and extend the line out to find our x-intercept, or when this delta V equals 0, or if you are given a formula like this, you can substitute delta nu equals 0 into this formula and calculate it mathematically. Now the other way, the second way we can do this is by plotting frequency versus 1 on n squared. The reason we do the 1 on n squared is just so we get the straight line. In the previous graph, the data points were a little bit off the line. This way, by graphing it in this way, all of those data points are on the line and it's much prettier. So what we're looking for here is we're looking for the frequency at which 1 over n squared equals 0. So instead of tracing down to find the y-intercept instead of tracing down to find the x-intercept like we did previously, we're tracing up here to find where the y-intercept is. So again, you can either extend your graph, or you can just again substitute 1 on n squared equals 0 into the formula given. So we found our frequency. What next? So we use the Planck equation. Now the Planck equation is in section 1 of your data book, and Planck's constant is in section 2. So Planck's equation, the Planck equation is the energy. So energy is Planck's constant times our frequency, which is given this kind of weird curly V symbol that's actually pronounced nu. So this guy here is nu, it's the Greek letter, and this is our frequency. We have Planck's equation, we have Planck's constant, which is in section 2 of your data book, and that is, if you'll just excuse me while I flip to my page, that is 6.63 by 10 to the negative 34 joules seconds. Now frequency is per second, and this energy here is in joules. So this is basically our way of converting between frequency of light and the energy of that photon. So this is the energy required in joules to generate a photon at that particular frequency. Now, so yay, I have my frequency. I can use my Planck equation to find out the ionisation for one atom, using that E equals h nu, like we did earlier. Then I can multiply by Avogadro's number to find the ionisation energy for 1 mole of atoms. Now, the bonus of doing it this way is if you are asked to figure out the ionisation for 1 mole of atoms, given a frequency, you go through these steps and your answer can be checked using section 8 of your data book. Okay, what else can you do? So you've got your frequency. You can also use another formula to go from frequency to wavelength of light. Remember, we use lambda to talk about wavelengths. Again, this is in your data book section 1. So we have our speed of light, and again, that's given in section 2, equals our frequency, which is our nu lambda. So our speed of light, again, that's a given number, and we can use this to convert between our frequency of light and our wavelength of light. Where that's useful is you can then use that to look at the colour of that light, for example, using the colour wheel on section 7 in section 17 of your data books. Or there's also a similar one in section 3, looking at the electromagnetic spectrum. So if you're asked what portion of the electromagnetic spectrum does such and such a wave belong to, you can use that electromagnetic spectrum or that colour wheel to figure out what type of wave we're talking about. Okay, so let's actually do some practice questions. So we're going to start with frequency and go to ionisation energy. So, a photon of frequency that is sufficient to ionise an aluminium atom. Calculate the ionisation energy of aluminium in kilojoules per mole. So our first step, we need to start with our Planck equation. So we have E, this pen is way too thick. We start with E equals h nu. So we have Planck constant, which is 6.63 by 10 to the negative 34, times our frequency, 1.4469 by 10 to the 15. Excuse me a sec while I calculate that. Okay, so the answer to E is 9.593 by 10 to the negative 19 joules. Remember, this answer's in joules. The answer I am trying to get to is in kilojoules per mole. So let's do the per mole part first. So the energy in terms of mole would be this answer times Avogadro's number, which is, okay, so we have 577,495 joules per mole. Now, that seems like a ridiculously huge number until you remember that I've got to convert it to kilojoules, which is simple enough. So the ionisation energy in moles would be, okay, so divide by 1,000, so 1, 2, 3. 577.495 kilojoules per mole. Now let's fix our sig figs. So I have 5 sig figs here, but only 3 in those two guys. So I need to take that back to 3 sig figs. So 577 kilojoules per mole. Now, give me just a second while I check up in the data book the ionisation energy. Okay, so according to our data books, in section 8 we have the first ionisation energy for aluminium in kilojoules per mole as 578 kilojoules per mole. Now, I say that there's enough agreement between those two answers, that I've checked it, and that looks right. Okay, so let's look at a slightly different way. Let's look at a slightly different way that you might be asked to use this Planck equation. Okay, so we have the ionisation energy of gold is 890.1 kilojoules per mole. Calculate the minimum wavelength of light that will ionise gold. So this is basically just the other way round. So you're given an ionisation energy in kilojoules per mole, and you need to take that back to your wavelength. So let's start by going, our energy per mole is 890.1 times 1000. Now remember, I'm multiplying by 1000 to get rid of the kilo in kilojoules. Then I need to get rid of my moles. So I need to divide by 6.02 times 10 to the 23. Excuse me just a sec. Okay, so I have my energy, and I've got rid of the moles now, haven't I? It's 1.4786 by 10 to the negative 18 joules. So I have my joules. So what I need to do next is I need to put that number into Planck equation. So I have, Planck equation is E equals Planck constant nu. So I need to convert that, so it is nu equals energy divided by Planck constant. So here's that E that I'm substituting in, and Planck constant is still that 6.63 by 10 to the negative 34. Excuse me a tick while I calculate that. So we end up with our nu is, or our frequency is, 2.230 by 10 to the 15 per second. So, but that's not what it's asking me for. It's asking me for wavelength of light. So to do that last step, I need to use that second formula that we discussed, linking frequency and wavelength. So we have C equals nu lambda. We're trying to look for lambda, so lambda is C on nu. I know my nu's, every time I draw them, are ever so slightly different. Just draw them as a slightly different V would be my tip. So our wavelength is C, which is the speed of light, which again is in section 2, and that is 3.00 by 10 to the 8 divided by what we figured out over the other side for nu, and excuse me just another second. So that wavelength is 1.345 by 10 to the negative 7 meters. The thing is, when we talk about light, we tend to talk about them in terms of nanometers. So nano is 10 to the negative 9. So that is effectively 134.5 nanometers. Now let's do another sig fig check. So H is only given to 3 sig figs, as is our speed of light. So our final answer has to be to 3 sig figs. So that's 135 nanometers. Okay. Thank you guys for being awesome. Please feel free to ask Mr. Chan or I if you've got any questions about this, and I'll see you guys in class. Bye.